Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This is part B of a lecture on solving quadratic equations using factoring. In this part, we're actually going to focus in on solving applications for quadratic equations. The applications we can solve right now are somewhat limited. However, we could still figure some stuff out. So let's go ahead and try our hand at some applications. Now, it's often the case that the applications at this point are somewhat trivial. In other words, they're not the best real world problems that you're going to face. And the reason why is because we can only rely upon factoring to solve these quadratic equations. However, as time goes on and we learn other techniques to solving quadratic equations, the applications we'll face are going to be a lot more complex. But for right now, let's go ahead and just see what we could do with the technology, the mathematical technology that we've developed thus far. Reading this out, one end of a ladder is 10 feet from the base of a wall, and the other end reaches a window in the wall. The ladder is 2 feet longer than the height of the window. And so now they're asking us to write a quadratic equation about the height of the window and solve the equations to find the height of the window. I've read the problem, so remember I have a problem-solving process here. And the problem-solving process is essentially the first thing you should do is read the problem, understand what's going on, and label unknowns is the next step. So I've read it, I understand what's going on. Generally, when you go for understanding what's going on, you should also draw a picture if you can. So let me go ahead and draw a picture of this situation. We have a wall. So I'll just say that's our wall right there. And we have a window set into the wall. Let's just pretend that this is our window right here. And so let me make sure that this looks like a wall. Not the best wall in the world, but whatever. And we have a ladder where one end of it is 10 feet away from the wall. So let's just, in fact, maybe I'll use a different color for the ladder. And one end is 10 feet from the wall, and the other end reaches the window in the wall. So it's this situation right here where you have a ladder leaning up, and somebody's going to climb up this ladder to reach the window. Now, there's something to be mentioned here that's not in the problem, but is usually implied in the problem. Nobody makes, unless you're in Italy, nobody makes a building that leans. And honestly, the Leaning Tower of Pisa wasn't made to lean, okay? So, this should be a right angle. That's kind of an implied piece of information. We know that this distance right here is 10 feet. I should probably put the units mark in there, 10 feet. And the ladder is 2 feet longer than the height of a window. Write an equation about the height of the window. So, we need to find the height of the window. I'm going to label the height as h. So h equals height of window. And I'm a big fan, actually, of labeling all my unknowns. So if h is the height of the window, the other thing we don't know in this situation is the length of the ladder. L is length of ladder. And I know that most instructors teach this to just kind of read this and immediately fill in the length of the ladder. But the reason why I like to take my time with it is because I want to introduce, or actually you've already been introduced to it, solving systems of equations. This is essentially going to be a system of equations. So now that I have this kind of set up like this, I can find a relationship between the variables and the number 10. The relationship is the Pythagorean theorem. Side squared plus other side squared should equal the hypotenuse squared. That's for a right triangle only. And of course I have one equation and two unknowns, so I need another equation, and that will come from this second sentence here. The ladder is 2 feet longer than the height of the window. So in other words, L is 2 feet more than the height of the window. Wherever I see an L in this previous equation, I'm going to replace it with 2 plus h. So that's what I'm going to do. So I get 100 plus h squared will equal 2 plus h being squared. That's a quadratic equation about the height of the window. And now the second part is just asking me to solve the equation. It says equations, it should be just equation. Solve the equation to find the height of the window. Okay. I see that I have to clean up the right hand side. So at this point, I generally forget about the word problem and I just concentrate on the mathematics here, the mathematical sentence. Remember that the quantity 2 plus h being squared means 2 plus h times 2 plus h. I will distribute the 2 through and the h through, and when you do that, you get this beautiful 100 plus h squared is equal to 4 plus 4h plus h squared. Now initially I think, oh, there's two different versions of my variable, and technically there are sitting here two versions of h. There's a single powered version and a double powered version. However, have some forethought here, be able to look ahead a little bit and notice that when you subtract h squared from both sides, they'll cancel out nicely and you'll get this wonderful equation 100 is equal to 4 plus 4h. Now that I only have one version of my variable, I don't have to move everything to the right hand side. I could just start solving for h. So I'll subtract 4 from both sides to get that 96 is equal to 4h, and then divide both sides by 4. H is equal to 24. And remember, we want to find the height of the window. We've just found it. The height of the window is 24 feet. Remember, we're dealing with units in feet. By the way, if somebody asks what the length of the ladder is, it's just 2 feet longer than that. The ladder is 26 feet. The next example here is that we have a box made from a square piece of cardboard. And of course, you're given a square piece of cardboard. You can cut out these corners. And so let me draw a picture of that so you can kind of see. If you have a square piece of cardboard here, not the perfect drawing, but good enough, it'll do. You can cut out corners. Cut out this corner, cut out this corner, and so on and so forth. When you do that, it allows you to fold up those flaps and you get an open box. Okay. So I just wanted to kind of show you that picture. So a box is made from a square piece of cardboard by cutting 2-inch squares from each corner and turning the edges up. So these are 2-inch squares. Alright, you get the idea. I don't need to do the whole thing. If the piece of cardboard is x inches square, which means that the length here is x inches. So the length here has to be x inches as well. Right. If the cardboard is x inches squared, write expressions for the length, width, and height of the box. Oh well. Let's see. The length of the box, we'll call that L, is equal to. Now, of course, when I write L is equal to, I really shouldn't do that. They're asking me to write an expression, not an equation, but an expression. So maybe I shouldn't write L is equal to here. Maybe I'll instead go ahead and just write an expression. The length is just going to be this length x, but we lose some of that length. When we fold up the edges, we lose 2 inches because of this rightmost edge and 2 inches because of the leftmost edge. So the length here, the expression for the length, is going to be x minus 4. The expression for the width, again, just using some logic here. The width, let's see, the whole width is x of the cardboard square, but we're losing 2 inches top and bottom, so that's the width. The height of the box, though, is kind of interesting. The height, well, if you fold up these corners, they're only 2 inches tall, so the height is only 2 inches. Now write an expression for the volume. Well, volume is just length times width times height. That's for a box. Volume is length times width times height. So that's 2 times x minus 4 times x minus 4. And let's see, part B, write and solve a quadratic equation to find out what size cardboard you need to make a box with volume 50 cubic inches. So part B here is just asking us, hey, how can that volume be 50 cubic inches? In other words, I want this volume expression here to be 50. And I remember I cannot just say, oh, therefore x minus 4 is equal to 50 or x minus 4 is equal to 50. I can't do that. What I have to do actually is distribute the x minus 4's into each other. So in other words, multiply those two binomials. I'm going to do a little trick first. You don't actually have to do this, but I'm going to divide both sides by 2. Just so that these twos cancel and I get 25 over there. You don't have to do that. I'm just doing it to kind of make my life a little bit easier during this process. Let's distribute through on those binomials. So you should get 25 is equal to x squared minus 8x plus 16. And let's subtract 25 from both sides because, see, we have an equation with two different powered versions of our variable. So we have to move everything to one side. So I'll subtract 25 from both sides. I get this business here. 16 minus 25 is negative 9. And hopefully that factors. It actually does. It factors to x minus 9 times x plus 1. So this means that either x is equal to 9 or x is equal to a negative 1. Think about this. X is a length, right? It's the length of this cardboard. So one of these solutions does not make sense, and that's often the case in physical situations, that when you're solving a quadratic equation that dominates or describes a physical situation, one of the solutions likely is going to fall out. It's usually the negative solution. Not that all quadratic equations have a positive and negative solution, but often it happens when you're solving applications. So our real answer is x equals 9. So the size cardboard we'll need is a 9-inch by 9-inch, or in other words, 81 square inch piece of cardboard. Now, before I do my last example here, I want to introduce another definition, and this definition is needed for the next example. Standard form of a quadratic equation. The standard form of a quadratic equation is this: ax squared plus bx plus c is equal to 0. That's what they call standard form. So you have an equation in x here, and it all equals to 0. It's just necessary for the following example. Examples: find a quadratic equation whose solutions are 2/3 and negative 2. And I'm going to tack on a little bit more. Written in standard form with integer coefficients. That's important for this example because it's very easy, although you may not think so yet, it's very easy to find the quadratic equation whose solutions are 2/3 and negative 2. In fact, if I told you I had a quadratic equation with solutions being 2/3 and negative 2, then you could say, oh, that means at the end of solving, you got the following: x equals 2/3 or x equals a negative 2. And that would be true. Of course, you could then say, listen, actually, if I want to rebuild the quadratic equation that you got, that you were given, so that you could have these solutions, I'm going to go ahead and basically move all values to the left-hand side. In other words, on this one over here, I'm going to add 2 to both sides, so I get x plus 2 had to be 0. And on the left-hand side, I'm going to write this, I'm going to multiply both sides by 3, so I get 3x is equal to 2. That's an important step. Get rid of fractions. And then subtract 2 from both sides. So 3x minus 2 is equal to 0. So these are the two objects that must have been multiplying to become 0. This means that either 3x minus 2 was 0 or x plus 2 is equal to 0, which means that when you multiply them, well, the product has to be 0. In other words, 3x minus 2 times x plus 2 has to be 0. Well, we're almost done here. If you distribute through, in other words, you multiply these two binomials together, you get the following: the 3x squared plus 6x minus 2x minus 4 is equal to 0. Or in other words, 3x squared plus 4x minus 4 is equal to 0. And lo and behold, I have a quadratic equation in standard form with integer coefficients. How did we do it? Well, notice in this problem-solving process, if I go back to maybe one of the previous examples here, in fact, let me go even back further. Let's see. This is from a previous lecture, but this is good enough. Notice that when you solve a quadratic equation, you start with a quadratic equation. Let's just focus in on this part right here. And then you try to factor it, and you get down to this beautiful factorization. And then you say, well, either the first object is 0 or the second object is 0, which means that v is equal to negative 3 or v equal to 6. What we did in our last example that we just did here is that we started with this bottom sentence. X is equal to, or in other words, v is equal to negative 3, or v is equal to 6. Move everything to one side, so v minus 6 is equal to 0, or v plus 3 is equal to 0. Well, if one of these two has to be 0, then their product must be 0. And if you multiply those things together, you get the original quadratic equation. So I want to point out one thing here. That in this process, there was a step in here that I kind of did a little bit of hand waving here. At this step right here where I said, oh, x is equal to 2/3, because they told me that's the solution, or x is equal to negative 2, I said multiply both sides by 3 to get rid of the fraction. If you didn't, you would get this: x minus 2/3 is equal to 0, or x plus 2 is equal to 0, which is fine. If one of these is 0, then x minus 2/3 times x plus 2 would have to be 0. But if you multiply this out, you're not going to get integer coefficients. You're actually going to get rational coefficients. X squared plus 2x minus 2/3 x minus 4/3 is equal to 0. These coefficients are not rational coefficients, or not integer coefficients. So by starting with getting rid of fractions, I avoided having to do fractional arithmetic. I avoided having fractions as coefficients. Essentially, I just got down to a point where I just had nice, beautiful integer coefficients. So that's just a hint for you. Make your life easy by getting rid of fractions early.